Hello students, welcome to today's lecture on artificial neural networks. Uh, Today we'll be discussing about another learning rule, which is error correction learning. In our previous lesson, we have discussed about the first learning rule, the oldest one, Hebbian learning rule. And also we have seen some examples of designing neural networks with the Hebbian learning rule. Today, we'll see error correction learning, how we can use this learning technique, learning rule for design of neural networks. So here is a simple introduction to the learning rule. Assume that the neuron is connected with some desired response, that is dk of n, and let the value, the actual output calculated by the neuron is yk of n. So I repeat, dk of n is the desired response from a particular neuron, and yk of n is the actual value calculated by that neuron at a particular time n. Okay, the neuron is k. Now we can calculate the error signal ek of n by subtracting the actual output calculated and the desired response expected from the neuron. Okay, so we can use this formula either in this way, yk of n minus dk of n, or dk of n minus yk of n. Either way you can use to calculate the error signal of a particular neuron k at time n. Okay. And the general purpose of error correction learning is to minimize the cost function, which will be based on ek of n, and the cost functions are several types. One example is given here, which is well known for the neural network designers, called as MSE, mean square error criteria, or cost function. J of n is equal to 1 by 2 into summation of ek of n, ek square of n, where k is equals to 1 to n, where k is equals to 1 to n. So this is a mean square error criteria for minimizing the error signal ek of n, which is based on the error signal ek of n. Okay. Then the neural network will be optimized by minimizing the j of n. The j of n is actually defined in terms of the error ek of n. Therefore, the neural network will be optimized by minimizing j of n with respect to the weights of the neural network. That means, based on the error term, we will modify the synaptic weights of the network in such a way that the error becomes minimized. Okay. So that is the main purpose of using this error correction learning. In error correction learning, this error term, the main objective will be minimizing this error term by adjusting the synaptic weights of the neural network. Okay. This difference weight to be added to the existing weight, synaptic weight of connections between neurons, will be calculated as eta into ek of n into xj of n. This eta is the learning rate that we will assume for a neural network, and ek of n is the error term that is calculated. It will be calculated by taking the difference between actual output calculated and desired response expected from a neuron, and xj of n is the input at time n connecting the neuron j and k. So by calculating this, then we can update the synaptic weight at time n plus 1 by using the formula wkj of n plus 1 is equals to wkj of n plus the delta wkj of n, where delta kj of n is calculated using this formula. This formula is called as delta rule. Therefore, error correction learning is also called as delta learning rule. And another name is also there, which is also this learning technique is also called as Woodruff's learning rule. So either error correction learning rule or delta rule or Woodruff's learning rule. You can call it in any name. Even in examination also, it can be given with any of these three names. So remember that you need to write the same algorithm for this question. Okay. So what are the three names? Error correction learning, delta rule, Woodruff's learning rule. So this is a pictorial representation of the concept that was explained till now. This is the black diagram of a neural network that shows the output neuron K. Assume that Yk of n is the actual output generated from this output neuron, and this is the desired response connected to this neuron, and Ek of n is calculated as a difference between this desired response and the actual response calculated. And this feedback, the error term is propagated back towards the neuron to update the synaptic weights based on this error term. Okay, that is what we discussed. The delta rule says that minimize J of n based on this error term propagated back. This is signal flow graph. You need to remember the signal flow graph of output neuron. It's important to draw this diagram compulsorily. It also shows the same concept. Yk of n is the output calculated from the neuron, and desired response dk of n is connected to this neuron. Ek of n is calculated as difference between Yk of n and dk of n, and this Ek of n is propagated back to adjust the synaptic weights connecting the neuron. Okay, so that's what the signal flow graph is showing. You need to understand that x1, x2, so on, xn are the inputs given to the neuron. WK1, WK2, WK3, so on. These are the synaptic weights connected to the corresponding neuron. These weights gets updated based on the error term calculated. That is the main concept used in error correction learning. With this introduction, let us go through the algorithm that will be used for designing a neural network that makes use of error correction learning. Step one of the algorithm is to initialize the weights and biases with some random values between 0 and 1. Okay. And then we'll use the formula of summation of xi wi to calculate the actual output of a particular neuron. After calculating the actual output of a neuron, then what we do is we calculate in step 2, we calculate the error signal of output neuron K during a particular time interval n using the formula Ek of n is equal to dk of n minus yk of n, the desired response minus actual output calculated. Okay, this we need to calculate as a sum of product of inputs and weights. Okay. In step 3, we'll calculate the weight difference, that is delta wkj, by using the delta rule. The delta rule says that delta wkj is equals to eta into error term into xj of n, where eta is the learning rate, which will be assumed as any value between 0 or 1. Okay. And in step 4, we'll update the weights by using the formula wkj of n plus 1, that is the new weight is calculated as the old weight wkj of n plus delta kj, which is identified over here, which is calculated using this formula. Okay. And once we update the weights, we will repeat the steps 2 to 4 until the error signal or error energy becomes as minimum as possible. You can identify this minimum by looking at the error energy or weights in such a way that there is no difference between the weights calculated in the previous epoch. Okay. So when we identify that the weights are not changed between the two consecutive epochs, we can stop the process and we can identify the weights of the neural network at that point. So this is the algorithm which we can use for designing a neural network that makes use of error correction learning. Let us understand this algorithm with the help of an example. Let us say we are going to use the truth table of AND gate. That means we are going to simulate the behavior of an AND gate by designing a neural network to identify the desired responses when we submit these inputs at a particular point of time. So if the input vector given to the neural network is 0, 0, then the desired response should be 0. If the input vector is 0, 1, then the desired response is 0. If the input vector is 1, 0, the desired response must be 0. If the input vector is 1, 1, the desired response must be 1. So to simulate this behavior of AND gate, we are going to design a neural network that makes use of error correction learning. And also we need to assume few things over here. We need to decide which activation function will be used for design of the neural network. So we assume that the activation function is a binary step function, which will be defined as some function of vk. Vk is the input given is equals to 0 if vk is less than or equals to 0. Otherwise, it will be 1. Okay. And also, we need to assume the learning rate eta is equal to some value between 0 and 1. So I will be assuming 0, this value as 0.1. And weights must be initialized to some random values between 0 and 1. We assume that W1 is 0.3, W2 is minus 0.1, bias is minus 0.1. You can take any values initially. It's not mandatory to take these values. Uh, these are random values only. Okay. Why is it W1, W2 and bias? Because the input vector size is 2, x1 and x2. Therefore, x1 is connected to the neuron with weight W1, x2 is connected to the neuron with the weight W2. And bias is as usual. It will be connected as a separate weight. Now let us consider the first epoch, how the values are calculated. I'm presenting this as a table. The first epoch considers all the input vectors and updates the synaptic weights based on the error term calculated for the previous input vector. Okay, let us start with the first input vector. I'm starting it with 0, 0. Okay, and the desired response expected from the neuron is 0. When the inputs are 0, 0, the desired response should be 0. And we will calculate the actual response from the neuron based on the initial weights we assumed. So the formula is activation function of x1w1 plus x2w2 plus bias. Okay, so therefore 0 into w1 plus 0 into w2 plus bias is 1 into minus 1. Therefore, it is going to be 0 when minus 1 is sent to the activation function. Binary step function results in 0 if minus 1 is the value over here. Okay, so the final value generated by the neuron is 0. Now, desired response is 0, calculated value is also 0, therefore error is 0. Okay, then there is no difference in W1, delta W1, delta W2 is also calculated by using this formula. Eta is assumed as 0.1, error is 0, and x1 is 0. Therefore, this delta W1 is also 0. Delta W2 is also 0 because error term is 0. Therefore, there is no difference between W1 and W2 as the assumed values are 0.3 and minus 0.1. Here also we got the same W1 and W2 since the error term is 0. So we continue to the next input vector 0, 1. Again, the desired response is 0, calculated value is 0 by using this formula. There is no difference, therefore error term is 0. Delta W1, delta W2 becomes zeros, and W1 and W2. The new values of weights will also be same because there is no error difference. Considering the third one, 1, 0, the desired response is 0. Calculated value is now 1 into W1, that is 0.3. This is W1 and this is W2. 1 into 0.3 plus 0 into 0.1, that is 0. 0.3 plus 1 into minus 0.1. Bias value is minus 0.1. Therefore, 1 into minus 0.1 is minus 0.1. So now it is 0.3 minus 0.1 is going to be 0.2. Whenever you say it is 0.2, if it is greater than 0, the output value is 1. Okay. Therefore, calculated value is 1. The desired response is 0. Calculated value is 1. Therefore, error term will be desired response minus calculated value, that is minus 1. Okay. Now we'll calculate delta W1. That is 0.1 into 1 into x1 is 1. Okay. 0.1. What is eta here? Eta is 0.1. 0.1 into error term is minus 1 into x1 is 1. Therefore, the result is minus 0.1. Delta W2 is eta into error term into x2. Since x2 is 0, this is going to be 0. Now the updated values are W1, that is existing W1 plus delta W1. Therefore, 0.3 minus 0.1, it becomes 0.2. It is minus 0.1 here, but delta W2 is 0. Therefore, there is no change in this minus 0.1. Now the weights are updated. Originally, it is 0.3 and minus 0.1. Now they are 0.2 and minus 0.1. Therefore, we consider these weights for the next iteration. The next input vector is 1 and 1. Desired output is 1, but the calculated value is 0 because 1 into 0.2 plus 1 into minus 0.1, that is 0.1, minus 1 into minus 0.1, the bias value. Bias is minus 0.1, remember that. Therefore, it becomes 0. Calculated value is 0. Therefore, the error term becomes desired minus calculated value is 1. Okay, 1 minus 0 is 1. So delta W1 becomes eta into error term into eta is 0.1 into error term is 1. 1 into 0.1 into x1 is 1. Therefore, it is 0.1. Delta W2 is also calculated as 0.1 into error term is 1 into x2 is 1. Again, it is 0.1. Therefore, we calculate the W1 as previous value plus delta W1, that is 0.2 plus 0.1, again it becomes 0.3. Previously delta 2, W2 is minus 0.1. Now we'll add it plus 0.1. It becomes 0 now. So the updated values, weight values are 0.3 and 0. Okay. Now we'll continue with epoch 2 since the error terms are changing. Until and unless we get all the error terms zeros, we'll continue the process. So epoch 2 is also using the same formulas. Again, we consider the input vectors 0, 0, 0, 1, 1, 0, and 1, 1. We calculate the actual outputs from the neuron. Desired response are going to be same. We calculate the error terms and we update the corresponding delta W1 and delta W2. Okay. So because this epoch also contains another term here, we'll continue with the next epoch also. For the next epoch, the updated weight values will be taken. They are 0.2 and 0. The formulas are going to be same as we did it in epoch 1. Okay. In epoch 3 also, we consider all the input vectors 0, 0, 0, 1, 1, 0, and 1, 1 with the corresponding desired responses, and these are actually calculated. Actual values are calculated here. And since the error terms, there are two error terms calculated, minus 1 and 1. The values are updated accordingly. And finally, at the end of this epoch 3, we got the values 0.2 and 0.1. Since this epoch contains two error terms, we continue with the next epoch also. Okay. Again, we start with the input vector 0, 0, and we continue the process for 0, 1, 1, 0, and 1, 1 with the desired responses and actual values calculated. And we update the weights whenever we get an error term other than 0. Okay. So now at the end of this epoch, we got 0.1 and 0.1. In this epoch also, one error term is identified. Therefore, we continue with next epoch, epoch number 5. Again, the process is going to be same. The formulas are going to be same. The input vectors are 0, 0, 0, 1, 1, 0, and 1, 1 with the desired responses 0, 0, 0, 1. And the actual values are calculated. Now you can see that the actual values calculated by the neuron is also 0, 0, 0, 1, which are same as desired responses. Therefore, all the error terms are zeros and there is no change in the weights. We started with 0.1, 0.1 and we ended with 0.1, 0.1 in epoch number 5. Since there is no error term identified, there is no error signal identified in this epoch, we can stop the process and the final weights of the neural network are identified. W1 is the 0.1, W2 is 0.1, and the bias value is not updated at all through these epochs, which is fixed as minus 0.1. Okay. Now the final neural network that is designed using error correction learning rule can be shown like this in a diagrammatic representation. This shows the neuron. X1 is the first input, X2 is the second input. The final weights we got in epoch number 5 is 0.1, W1 is 0.1, W2 is 0.1, and bias is minus 0.1. And this O represents the output, the actual output from this neuron. Summation indicates how you are going to calculate the output of the neuron, and this shows the activation function. Okay. Now you can test this neural network for a given uh, input vector. Let us say I am considering this one 1, 0, 1, 0 as input vector. X1 is 1, X2 is 0, and I just want to test whether the neural network will calculate the output as 0 or not. Okay, so X1 is 1, X2 is 0. Now we'll calculate it as 1 into 0.1, that is 0.1, plus 0 into 0.1 is 0, 0.1, and 1 into minus 0.1. Therefore, 0.1 minus 0.1 becomes 0. Okay, and the final output is 0, which is the expected value from the neural network. Okay, even you can test it for 1, 1 also. If the input vector is 1 and 1, the desired response should be 1 from the AND gate. Now let us test it with the help of x1 as 1 and x2 as 1. 1 into 0.1 plus 1 into 0.1, which is 0.2 minus 0.1. Then it becomes 0.1. If it is sent to the activation function, because it is a binary step function, 0.1 means that it is 1. Okay, as I told you, if the input given is greater than 0, then the output of the activation function will be 1. Because it is 0.1, vk is 0.1, the output becomes 1. Okay, so in that way, the neural network produces the output as 1. Right. So we can say that the AND gate behavior is simulated properly with the help of a neural network by using this error correction learning rule. Right. So I hope you understood the error correction learning rule. Now here is an example exercise uh, to test yourself whether you understood it properly or not. Design a neural network for simulating the OR gate behavior. That means you are going to take this truth table 00011011, but the desired responses will be 0 here and 1s here, except when x1 and x2 are zeros, the desired response is 0, and remaining cases, the desired responses will be 1. Okay, so you consider that truth table, and also you can assume the same binary step function over here. You can assume the same learning rate. You can start with these initial weights also. So you can consider this same values just like the previous example, and design the neural network for simulating the behavior of our gate. Okay, so that's all for today. Hope you understood the concept. Uh, in our next class, we'll be continuing with the remaining part of learning rules. So till now we have discussed two learning rules. One is Hebbian learning rule and the other one is error correction learning rule. The remaining two, memory-based learning and competitive learning, will be discussed in the next session. Thank you all for your patient listening. See you again in the next session. Thank you all.